In this problem, we see that there are two current carrying wires. One is carrying current I1, and the direction of the current is coming out of the page, and the other current is I2, which is going into the page. Now, remember, these two will project magnetic fields in a circular manner, and the direction of the magnetic field will be given by the right-handed grip rule. So now, you in the first part, in part A, you are asked to find out the expression of the magnetic field at the origin, right? So now if you apply the grip rule for I1, you would have basically a magnetic field direction like this, right? So this will project a magnetic field direction in the y-axis, right? In the positive y-axis at the center, at the origin. Similarly for I2, if you apply the grip rule, the direction will be like this. So this will project a magnetic field uh, direction in the positive x-axis, right? So this is because of I1, so I term this as B1, and this is because of I2, I term this as B2. Now, what's the net net magnetic field direction? So that's like B1 in the positive y-axis direction and B2 in the positive x-axis direction. So my net magnetic field direction is somewhere in the xy plane, right? So that's my B. So now I will have in the expression of the magnetic field B, I would have a contribution from both I1 and I2. And since this is a line current, the expression is basically just mu naught I by 2 pi r. So basically for I1, the contribution I have, which is B1, B1 in the positive y-axis direction. So that's like mu naught I1 divided by 2 pi r, right? And the distance between the current line current and the origin is d1, so I just term this as d1 in the positive y-axis direction. And for I2, that's mu naught I2 divided by 2 pi d2 in the positive x-axis direction. So that's my expression for B, right? Okay, so in part B, part A, so that's like you have a subsection. So they have shown you that we have a magnetic field into the page, which is a time varying magnetic field, right? So that's changing with time, and it's changing sinusoidally with time, right? And we have to find out the flux phi B through this area, right? Square shaped area of 10 by 10 centimeters, right? So that's like very easy. So we know that my flux through an area is given by basically the double integral of B dot dA, and in this case my basically this is the integration of the area, right? So I know my area, which is this much, right? So this is basically B times A, right? So now what's my B? My B is basically 1 by 200 pi sine 2 pi t. And what's my area? That's like 10 centimeter by 10 centimeters. So I just convert them into meters. So that's like 0.1 into 0.1. So that will give me a phi B of sine 2 pi t Weber, right? So that's my phi B, right? So you see it's also varying sinusoidally. Now for the part B subsection, they have asked like for the same problem to determine the magnitude of the induced EMF in the wire loop as a function of time. So in the previous section, we found out that because of the time varying magnetic field in this loop of the time varying magnetic field inside this area will generate a flux phi B, which is given by this expression. Now this will induce a magnetic field, will induce some voltage, and that will cause a current flowing into this loop of wire, right? So I'll just start with the part B here, right? So I'll just write the expression of phi B again. All right. So now I have to find the induced EMF So we know from Faraday's law that the induced EMF, the magnitude is basically minus n d phi b by dt, and the minus sign is because of the Lenz's law, right? So that's like opposing the change that causing the induction. And since this is a single wire loop, my n is equal to 1, right? My n is equal to 1. So that's a single wire loop. So basically my induced EMF is gonna be, since it's modulus, I don't have to worry about my sign right now. So d by dt phi b. So I'll just plug in the phi b value here. So if I do the differentiation, I will have this sign to be cos, and I'll have 2 pi coming outwards and multiplying, right? So I will just end up having cosine of 2 pi t multiplied by the 2 pi, and this will just cancel out to give me my induced EMF to be, yeah, the pi will cancel out, right? So this will be cosine. So basically you see my flux varies by sinusoidally, but my induced EMF varies in a cosine manner, right? So now in the third part C, you have to find out what's the direction of the current, right? So this is the induced EMF, right? But remember, this induced EMF is a time varying function, right? So it's changing with time. So therefore, since this is changing with time, therefore the induced current direction is also changing with time, right? Why, we'll just see in a bit moment later. So you have to find out the direction of the current of the loop in this time, between this time, right? So since our induced flux is sinusoidally varying, right? So that's like sinusoidally varying sine 2 pi t, right? So this is, I can write this, let's say I can write my phi b, right? I can write my phi b is a function of sine 2 pi t, right? So this is basically my omega t, which is basically the theta, right? This is the angle theta. This is radian per second, and this is into time. So that should give you in this time, if you have an oscillating function that's varying, let's say this much omega radian per second. So in the time t, how much theta you will progress, right? So that's we can use here. So basically, you have to find out the direction of the current in this time interval, 0.25 seconds to 0.5 seconds to 5 seconds, right? So since my omega is 2 pi, as we know from the phi b, so that should give me my theta, right? So that's like omega t. So I'll just multiply omega, right? I'll just multiply omega, which is 2 pi, and I'll just multiply this into t. That should give me my theta, right? So I'll just do omega t, so 0.25 into 2 pi. That should give me a value of pi by 2, and 0.5 into 2 pi, that should give me a value of pi, right? So I have to look for, in this region, what's the direction of my current, induced current, right? So now remember, the direction of the magnetic field or the flux is into the page, right? Now it's varying also sinusoidally, as we have seen here, right? It's varying sinusoidally. So if we draw sinusoidally, right? If we draw sinusoidally, I draw from one time period, omega t, and I just draw this, let's say, by B, magnetic flux Tesla, magnetic field Tesla. So this since is varying sinusoidally. So this is my 0, this is my pi by 2, this is my pi, this is my 2 pi, right? So I have to look which region. I have to look in between pi by 2 to pi. So that's like this region, right? So in this region, you see my magnetic field is decreasing, right? It's decreasing into the page, right? So what's my phi b? My phi b is also decreasing, right? My phi b is decreasing into the page. So now by Lenz's law, remember by Lenz's law, it should try to oppose the change. So therefore, a current will be induced in the loop, right? A current will be induced in the loop such that it opposes the change. Now, what's my change? My change is the flux is decreasing and the direction is into the page. So the change should be my induced current should try to increase this flux, right? So oppose the decrease. So it should try to increase this phi b. So that means the direction of the induced flux should also be in the same direction, right? The phi b induced should also be in the same direction. So such that it would sum up to cancel out the decrease, right? So if I apply the right hand grip rule and if I point the thumb inside the page, I would have a current direction, I would have a current direction uh, clockwise. All right. Now, let's say if you want to look into the other thing, like for example, if you want to look into this portion, right, where my magnetic field is increasing, right? So my magnetic field is increasing, that means my magnetic flux is increasing, right? So in that case, if my magnetic flux, let's say if my phi b is increasing into the page, so my induced phi should try to reduce this change, right? Should try to decrease this. So my induced phi b should act in the opposite direction to cancel out, right? So now for that one, my current direction would have been in the anti-clockwise direction, right? The induced current direction. So that in that case, it will have a magnetic field, induced magnetic field direction coming out of the page, which is trying to decrease this increasing magnetic field into the page.